Hello students. Now this discussion is also known as zero signal collector current and zero signal base current. So from this previous class, the biasing means the proper flow of zero signal collector current and proper maintain with the base emitter voltage and base collector voltage, and also the base emitter junction keep to in forward biased and base collector junction is also reverse biased for acting operation of transistor. Now in the value of IB, that is the zero signal base current, that is the equation number 1, and IC, that is the beta IB. Now this IB, this is the value of IB. Now put this equation from multiply with beta, then we get a IC. Now this is the equation number 2. So we calculate the emitter voltage. Now the DC analysis, for DC analysis in a DC bias of self bias condition of transistor. Now the voltage at emitter point BE. Now BE is equal to IE RE, because in emitter circuit a resistor, that is the RE, connected with the emitter terminal. Now in emitter terminal resistor dropped by the passing of emitter current, then this drop of voltage is known as emitter voltage, that is the VE equal to IE RE. Now we also known in previous class the IE is equal to IC. Now we put this value VE is equal to ICRE, that is the emitter voltage, that is the ICRE. Now the equation number 1 and equation number 2, now that is the emitter voltage for the applying voltage, that is the emitter voltage. Now again we calculate the emitter collector voltage. Now emitter voltage junction, that is the VCE. Now we calculate as VCE. Now in this voltage, that is the voltage from collector to emitter. Now in calculate the VCE, now we consider as transistor connected in a output loop, we consider as output loop. Now apply the KVL at output side. Now we write as the applying KVL at output side. Now according to KVL, that is the output side means VCE path, that is the VCC minus IC dash RC minus VCE minus IERE. Now we write as VCC minus IC dash RC minus VCE minus IERE equal to 0. Now VCC minus, now in a previous discuss the IC dash is nearly equal to IC by replace of IC in place of IC dash. Now we write as IC RC minus VCE minus ICRE, that is equal to 0. Because of IE is nearly equal to IC in previous discuss, that is the IE is equal to IC. Now we replace IC in place of IE and IC in place of IC dash. Now again VCE. Now this is the negative term as sided to right hand side, then we also get VCE equal to VCC minus ICRC minus ICRE. Now again the same term, that is the IC and IC, now we taken from common in both terms, that is the IC. Now we get VCE equal to VCC minus IC, that is equal to RC plus RE. So this is the value of VCE. Now this is the zero signal base emitter voltage. This is also called, this is also called zero signal collector emitter voltage. Now this is also called zero signal collector emitter voltage, that is a VCE. Now this voltage is we get from this model, that is the VCE, by without applying any input signal. So when we not applied any signal but we get some voltage from collector to emitter circuit, that is also known as zero signal base emitter voltage, that is also known as biasing of a transistor. Now VCE equal to VCC minus IC RC plus RE. Now we write from this equation number 3, that is the VCE equal to IC VCE, that is equal to VCC minus IC RC plus RE. That is equation number 3. Now again we analyze the voltage at point A collector. Now voltage VE equal to IC RE. Now now we calculate the voltage at collector terminal VC. Now we calculate the VC. VC means that particular point voltage is known as Vc. So we know Vce equal to Vc minus Ve. Now we know Vce equal to Vc minus Ve. So here Vc equal to Vce plus Ve. Now this equation, this negative voltage or a Ve or a Vc equal to Vce plus Ve. Now we put this value Vc equal to Vce, that is the value of a Vce, Vcc minus Ic Rc plus Re minus Ve, that is the value of a Ve, that is the equation number IV 4, that is the put this value ICRE. Now we remove this bracket, then we get Vc equal to Vcc minus ICRC minus ICRE, that is the plus signal, that is the plus ICRE. Now in this value, this is the ICRE, this is the ICRE, plus minus, that is the cancel. Now we get Vc equal to Vcc minus ICRC. So this is the voltage in point of a collector. Now this point of voltage, that is the Vc. Now this Vc, the value of a Vc is equal to Vcc minus ICRC. Now again we write as equation number 5, the Vc equal to Vcc minus ICRC. So this is the voltage at point, collector point. Now we calculate again the next voltage now at point B, at base point, that is the voltage from base point, that is the Vb. Now in this circuit, that is the Vbe, that is the plus and minus. Now base emitter voltage. Now we find out the voltage from base voltage, that is Vb. Now we calculate Vb, but we know Vbe, we know that Vbe equal to Vb minus Ve, Vb minus Ve. Now Vbe equal to Vb minus Ve, because that is the base emitter voltage, that is the junction, base emitter junction. This voltage is known as the difference of base voltage to emitter voltage. Now Vbe equal to Vb minus Ve. Now Vb equal to Vbe plus Ve. Now we know as base emitter junction, that is a doping of a base emitter junction, that is the PN junction. Now Vbe means the base emitter junction of a silicon transistor as a 0.7 volt. Now we write as Vb equal to 0.7 volt plus Ve for silicon transistor, but this value of Vb, that is the 0.3 volt plus VE for germanium transistor. Now we calculate the VB equal to 0.7 plus VE for silicon and 0.3 volt plus 0.3 plus VE for germanium. Now this is the equation number 5, this is the equation number 6. So these are the all about or all details of biasing in DC model of self-bias method. Now self-bias method means DC biasing with feedback voltage from collector circuit. Now we calculated as the zero signal collector current and zero signal base current and zero signal base emitter junction voltage and zero signal base emitter junction voltage and analyze all voltage in a base point, collector point and a emitter point. This is the biasing for transistor, and again we discussed the DC load line. Now we again discuss DC load line. So this load line is a curved line or inclined line, that is the in a graphical representation in voltage versus current. Now we write in x axis, that is the voltage axis, that is the VCE, and in vertical axis, that is the current axis, that is the IC. Now that is in a milliampere and that is unity volt. So this model or this graphical representation of base voltage of a collector emitter and the current in a collector current, the graphical representation or line, that is known as DC load line. Now in this line, that is this load line touches or reached or touched or intersect at a point of x axis at point A, and this line intersected the vertical axis in point B. Now we calculate the value of point A. Now that is a graphical point or a geometrical point. Now we calculate this point when we point out this point, that is the V and I. Now voltage and current, that is the point. Now we calculate by applying the equation number 3. Now from equation number 3, in this point at point A, the current must be 0. Now in this point the current axis are vertical axis. Now this point are lie in the x axis, that is the IC is 0. Now VCE IC point, that is the 0 at point A, 0 and we calculate the VCE. Now put this value of IC in equation number 3. Now put this value in equation number 3. From equation number 3, that is the VCE equal to VCC minus IC into RC plus RE. So here the IC means collector current is equal to 0. Now this value of a collector current put in this equation. Now we get the VCE equal to VCC minus IC means 0 into RC plus RE. Now this value is multiplied with 0, that is the 0. Now VCE equal to VCC. Now this point we write as this point A, VCC 0. VCC 0. Now we calculate the point, geometrical point at B point. Now we write as that point voltage or VCE must be 0. And this value of VCE, put this equation number 3, then we calculate to get IC. Now we put from equation number 3 VCE equal to VCC minus IC into RC plus RE. Now put this value, VCE is 0. Now at the point of vertical line, that is the VCE is the 0. Now we put this value 0 equal to VCC minus IC whole into RC plus RE. Now again we calculate as VCC equal to IC whole into RC plus RE. Now again we calculate IC equal to VCC divided by RC plus RE. Now this point of IC equal to VCC divided by RC plus RE. So that is the geometrical point represented as point B, and a geometrical point represented as point A. At point A, that is the point VCC 0 and the point B 0 and VCC by R1 plus RC plus RE. So the intersection line of a transistor characteristic curve. Now we draw the transistor characteristic curve. Now this transistor characteristic curve are intersect at point to the DC load line, that is the point as known as Q, that is the operating point. Now we write this equation, this point as VCE Q, and this point is represented as ICQ. Now we write as a DC load line. We write as a DC load line means the operating point. Now we write as operating point, operating point means Q. The intersection of DC load line and VI characteristics curve is known as operating point. that is also known as Q point. Q point. Now this point is known as VCE, VCEQ and ICQ. So this is the known as operating point. Now when the zero signal collector point, the zero signal point of operating point VCEQ and ICQ is also be known as operating point. So this is the self bias model or self bias configuration. Now next discuss last one, that is the third method, that is the voltage dividing method or voltage divider process. So in three method of biasing of transistor is also applying in a properly amplifier circuit by the process of amplifier modeling or DC modeling. Now in next class we discussed in a voltage divider biasing method.